is not my specialty. So my name is Luke Carter. I'm here from the University of Birmingham, and we're talking about laser powder bed processing of refractory materials and a couple of other things as well. At this point, I'd like to give full credit where credit's due. First to Alberta, who was with us a little while ago, but really kick-started our work on molybdenum some time ago now. So she's seen AMAZE from a couple of different viewpoints, which I guess has been quite nice. And to our ongoing PhD student, Amanda Field, who's doing that PhD with CCFE. So this relationship sort of carrying on beyond AMAZE, which is really, really nice to see. So basically, I'm going to give a very brief overview of the high heat flux demonstrator, just because Dave's just been talking about it. A little bit about our powder bed equipment, just to sort of set the scene. Then the work we've done on the three materials, vanadium, molybdenum, and tungsten. And then a little bit about some of the trial work we've done on some of those bonding methods, which might be of interest to CCFE in the future. So, as you've just heard Dave describe, this is the sort of the concept for that demonstrator, this millipipe design, where you have some kind of plasma-facing surface at the top, which obviously is high performance, and tungsten's the obvious candidate for that. And then some kind of structural material below, which is carrying this coolant, which we were looking at most potentially being molybdenum, which was where we were focusing. So we were looking at these refractory materials. And I guess the advantage that additive brings at this point is the complexity of that design they could have in the future that could be brought in, just from sort of a design freedom point of view. So at Birmingham, all this refractory work has been carried out on our Concept Laser M2 machine. You've had a full day of these presentations, so I'm pretty sure you're familiar with the whole family of machines by now, but it's a 400-watt system. It's got pretty standard build area, 250 by 250 millimeters and about 280 millimeter depth, so it's not one of these massive scale machines, but it's not one of the teeny tiny machines either. It does most of our work at Birmingham, really. It's very versatile. We have a reducer kit, so we can use small volumes of material, which is particularly useful for the refractory materials, and we maybe don't have so much or don't want to sort of weigh the machine down with kilograms and kilograms of tungsten, because it's quite heavy stuff. And obviously it's processing under an argon atmosphere. So I'm going to start off with the work we carried out on vanadium. This was some time ago at Birmingham. It was basically a pretty quick parametric study, just looking at the feasibility of using vanadium. It showed relatively low porosity throughout a large processing window. There is some grain-bounded cracking present in the material. The refractories are notoriously brittle at room temperature and susceptible to oxygen pickup and oxygen embrittlement. But it was quite nice, and as sort of part of this work, we produced a thermophysical test plate for CCFE. We're going to run a whole load of tests and hopefully get a nice little publication out of that in the near future, because it's quite novel. I don't think many other people have processed vanadium by laser powder bed. It was sort of ultimately rejected early on due to higher tritium retention. Apparently it was incompatible with the proposed coolant. Again, this is all fusion side of things, so maybe Dave will be able to answer your questions on this, I'm not sure. And also, you know, it's relatively low melting point compared to tungsten at about 1900 degrees, I think, for vanadium. But there's still maybe some interest in the future, which is why we've done this thermophysical test plate, and it could be of interest in the future. So it's well worth mentioning. Just to kind of prove concept that yes, we could make potentially some kind of complex design. This was well before we had any idea what the millipipe design was going to look like. We just basically made a block and put some small channels in it and said, look, we can do small channels in a block of vanadium if that's the kind of thing you wanted. But it sort of proved the concept pretty well. These little millimeter tubes we put through the vanadium piece. So it was quite a nice little piece of work there. And there's that test plate that I was talking about, which we passed over. Was that tested at Swansea? I'm not sure if it was. No, maybe it wasn't. It was at CCFE. Okay. Moving on now to molybdenum. So this suffers a similar sort of low ductility at room temperature as a sort of common with refractory materials, so it's quite challenging from that point of view. It's prone to cracking, basically, and rupturing. It's apparently more appropriate compared to vanadium, although it is still susceptible to activation. There's been a lot of talk about whether you can have selective isotope selection of molybdenum to use the more favorable isotopes for the application, and that's kind of still ongoing, but it is of interest as a structural material. We actually had 3 different powder batches for this, and it's quite interesting to look at where we can look at powder back to back. You know, we don't often get the chance to take different batches of powder of the same material and say, well, you know, which powder's better, basically. And I'm sure, as you're all aware, that supply chain and powder quality is really being discussed quite heavily at the moment, and is really important in the quality of your final part. So it's quite nice to be able to do that. So here are those 3 different powder batches. We had 2 from TLS, which showed quite a lot of fine. They didn't spread very well in the machine. The fine tends to agglomerate the powder a little bit, sort of cakes up. And then we had sort of a nice spheroidized powder there on the right-hand side from Techna. When we carried out our parametric study, so here's some basic Archimedes density measurements with those 3 different powders presented sort of back to back with just, again, simple linear energy density. So this is just the power over the speed. But it illustrates that the nice spherical powder, the Techna powder, was sort of outperforming the other 2 in terms of just porosity pretty consistently. It's illustrated a bit better if you look at the individual graphs, the different powers. So there on the left-hand side, you've got the 300 watts with scan speed across the x-axis, and that Techna powder is sort of always showing a slightly higher sort of level of consolidation. And likewise, not as clear with the 400, but yeah, with the 400 as well, it's still above the other 2 curves, which kind of confirms what you imagine, that sort of nice spherical powder in the size fraction that you want is going to give you a low porosity material. The material does crack, and there's not a huge amount that we can do about that with the technology in its current configuration. So basically sort of echoing what Dave was saying, we've got to a point where we're saying, look, we've reduced the porosity, we've reduced the cracks as much as we can with the machine in its current configuration. And Amanda's work is going to carry on with these refractory materials and try and modify the process and do some, I guess, process development type work to try and reduce that cracking further. But for the purposes of AMAZE, we got to this point and said, well, we're going to have to produce you bits based on this at the moment to see how good it is and whether you can accept some of these defects. And we've heard that a number of times, I think, today, whether defect levels are acceptable within your usage. I'm just going to mention this point that we've quite recently repeated a couple of those parametric studies. It's been a bit of a life lesson. We had a slight problem with our laser. Some of the optics were a little bit worn, I guess, and we were having a problem with beam defocusing, which we picked up sort of towards the end of last year. So sort of just to confirm our initial Moly results, we repeated some of that parametric study, which shifted the processing window a little bit, because now we've got a slightly more consistent focus at around sort of 60, 70 microns in size. But we're still sort of seeing the same types of defects. We're still seeing the same sort of types of porosity and the same level of cracking, really. So it hasn't changed anything hugely. But it is maybe a lesson that we learned, that we've got to really monitor the health of our laser and our systems. And we hope that machine manufacturers will sort of take that on board, and sort of in the future we can maybe see more on-board analytical options to keep an eye on those sorts of things. So we produced some very simple parts. You can see here is a block with a tube through it, very similar to what Dave showed in copper, but this is in molybdenum. And we produced some of these square, they're basically just sort of blank end caps that you can braze a pipe onto. And these were for pressure testing, just to see if the molybdenum was going to withstand the pressure of the coolant in the high heat flux rig. Unfortunately, it didn't with the cracking there. They leaked, so we weren't able to continue that high heat flux testing any further. But we have been sort of throwing around a number of ideas at how we might be able to retrofix this problem, possibly through hipping, possibly a couple of other options there as well. So all is not lost yet. So I think it's a pretty good result that we can produce a part, and it's pretty much fully dense. It just needs to have those cracks eliminated, really, or reduced significantly. Moving on to the tungsten, which is sort of, I guess, the current focus of our work. Some of this is, as I said, part of Amanda's work, and it's ongoing. It's a very challenging material, again, as I'm sure you're aware. It's got this ductile brittle transition, so it's not really ductile until and again, it depends on the oxygen content, but I guess if you want a really rough ballpark figure, a few hundred degrees, 400 degrees maybe. Above that, you start to get some ductility in the material. Below that, it's brittle, so it's going to crack at room temperature under residual stress. It's very prone to oxygen embrittlement and has low oxygen solubility, so the oxygen tends to go to the grain boundaries and form sort of brittle regions there, basically. And of course, it's a high melting point material, and a lot of the early papers that were published on tungsten used tungsten powder with a binder material, so a low melting point binder, so they were sort of not melting the tungsten, they were just melting the binder and sort of creating a dense part through that. With our 400 watt system, we're actually melting the tungsten, so this is pure tungsten that's being melted and consolidated. And it's only really in recent years those high power machines have become sort of common enough that we can start to look at this as a viable option for making shapes in this material. So once again, we had two different powders. Powder on the left, it's formed by some kind of chemical reduction method. It's sort of faceted and not really what you want to be putting in your powder bed machine. And then we've got a sort of spheroidized powder on the right. But it is always nice to compare these back to back. As you imagine, a similar sort of study here. You can see the blue line there is our nice spherical powder, which in terms of density is always outperforming that faceted powder. And we believe that just to be purely packing in the powder bed, we're just getting too much argon trapped between the powder particles that's just being converted into porosity eventually and unable to escape during the melting process. Just so you've got an idea of what this looks like, I would like to say at the moment, I've put up some micrographs. Micrographs of tungsten currently sort of carry the caveat that it's a very difficult material to prepare for microstructural analysis, especially when it's this cracked. One of the reasons why Amanda stuck with Archimedes density testing is because she had such trouble preparing the material. So some of this porosity that you're seeing here might simply be being grains that are being sort of ripped out during the sample preparation process just because it's so cracked at the grain boundaries there. So it is a difficult material to prepare. And likewise, the polishing solution just loves to sit in those pores and then scratch your sample when you're trying to go down to finer and finer levels. So it's a tricky material to work with from lots of different points of view. But you can see there, two different powders, same processing conditions, and you've got quite a startling difference in what's coming out at the end of the day. This is a very recent study, and it is kind of ongoing. But it's to highlight a particular point. So we heard earlier from, Alberta definitely mentioned it, and a couple of other people have talked about energy density, volumetric energy density, which is it's a way of getting a single parameter from your power, your speed, your hatch spacing, and your layer thickness of your powder. And we sort of combine those all together and come up with this volumetric energy density. And it is certainly useful for some materials, but this is a cautionary tale. So all the points here, so these are different plots, but of the same points. All the points here were processed under the same volumetric energy density. But you can see there's a huge variation, so it's not necessarily appropriate for this material. You can see that on the power side of things, you're kind of seeing a threshold there about 250 watts, but beyond that, you've got these layers, so basically it's kind of showing that power is not really having such an impact after that 250 watt level. The trend sort of downward going with scan speed, as you might expect. The faster you scan, the more porosity or the lower the density of the material. And then this bottom right one here is, just to confuse everything, is density plotted against global energy density. And this is one of the ideas that we're starting to pick up now is maybe there are other combined parameters which are a bit more appropriate. Global energy density is a combination of the power, the speed, but this time the beam diameter. So it's more similar to a linear energy density, and this seems to show a really strong relationship. Now, I'm not saying that this is a complete study yet, and there's still a lot of work to be done just to kind of verify that we're doing this correctly, but it is a cautionary tale about using volumetric energy density too widely and too confidently without appreciating that some of the detail is lost as soon as you start combining parameters. Just to give you an idea, these are sort of fairly low magnification optical images, but the image on the left there is our sort of current best, if you like, with tungsten at the moment. And Amanda's work at the moment is focusing on really trying to get to the root cause of this cracking behavior. So she's been doing some work here, which is looking at single scan tracks just on tungsten plate to start with, to try and identify processing windows where we're seeing this centerline cracking. Centerline cracking, of course, quite common in welding literature, where you see this sort of big centerline grain boundary forming a weakness down the center of the weld. And I think with tungsten especially, just given how messy the additive manufactured produced part is, it's worth going back to basics. You know, whenever we do metallography on additive parts, it's always a little bit like archaeology. You've got, you know, hundreds, maybe thousands of layers all on top of each other with possibly hundreds of thousands of laser scan tracks and defects building up on each one. So it's very difficult to work out what's going on. So a little bit of fundamental work is certainly justified in this case. As you can see, I mean, as you know, we're sort of just confirming this is grain boundary cracking here, but have I got a cursor? I sort of have, it's a bit delayed. You can see we've got some sort of centerline cracking here and this kind of chevron cracking, which corresponds to our grain structure. So it's kind of where we'd expect the cracks to open up. And there's talk of doing things like an atom probe to really get to the root cause of what's happening at those grain boundaries, and hopefully propose some ways of getting around it once we understand it better. So once again, we've produced some parts for CCFE. There's some little bending samples and some thermophysical samples. The point of these tests is really so CCFE can try and benchmark the additively produced material against traditional material. So we're sort of passing those samples to them as part of AMAZE. We've also made these big flat squares, which are the armor tiles that Dave was talking about, and we're hoping those are going to be tested in the near future, and we've got our fingers crossed that we'll have at least some promising results that they stand up under test. So we're quite hopeful about that. As I've sort of hinted at, this is ongoing stuff, but we're looking at developing a heated powder bed, so we can raise that kind of background processing temperature, preferably to above the ductile brittle transition. So maybe we can try and avoid some of that brittle fracture, but then of course the question arises, what happens as soon as you let the bed cool down, because you have to at some point. We're also looking at maybe some of the root causes stuff, control and monitoring of oxygen. The concept laser system operates under an argon atmosphere, but realistically it's only getting down to about 40, 50 ppm after purging for a while. It's a simple purge system, and we've done some independent monitoring on that. But we could look at improving that in some way, maybe some sort of getter or better way to reduce the oxygen in the atmosphere. And then further processing mapping work is kind of going on, and there's even the possibility of doing some in situ alloy development that's similar to the sort of stuff Nick was talking about earlier. Pretty briefly, I'm going to talk about some of the bonding trials we did. So we looked at two different ways of bonding, which were a bit novel, and these were really quick, just sort of testing the water stuff. But again, we're kind of hoping that in the future they might be of interest to CCFE. We looked at hip diffusion bonding between molybdenum and tungsten, and just the direct laser beam melting of molybdenum on tungsten. So essentially start off with a tungsten substrate and then build a complicated molybdenum part on top of that to form your millipipe design. The hip diffusion bonding, I think Alberta did this one actually. Was this? Did you do this? You did do this. Yeah. Must have been towards the end of what you were. So basically, it was a pretty simple experiment. We had these little buttons of molybdenum and tungsten. We had a steel preform. We popped the buttons in, then we welded some sides on the hip can, evacuated all the gas from it, popped it in our hipping chamber, subjected to high temperature and pressure, and then just sectioned through it and just had a quick look to see what the bond looked like. It's not a very exciting micrograph, but there didn't appear to be any huge defects in that bonding region. So we're pretty hopeful that might be of interest in the future. We didn't get any further than that, so we haven't tested it or anything like that. So there's no sort of mechanical tests available for that bond at the moment, but in the future it might be something that's interesting. And then secondly, we popped a tungsten base plate in and we tried to build some molybdenum on top of that, melt molybdenum on top of that. We saw sort of a really nice kind of mixing sort of interface region here. It's kind of got this sort of swirly pattern where we saw some obviously mixing and melting of both the tungsten and molybdenum. It was quite a nice experiment from that point of view. A few of the more observant of you may have noticed a couple of cracks just there in the tungsten base plate. Very recently, we've actually looked at this plate that we have, this kind of I guess it must be rolled plate of tungsten, and there do seem to be defects just below the surface of the rolled plate. Obviously, these are a little more prominent than maybe we're seeing in the roll plate itself, but it could be that the residual stress is kind of just opening up those defects in the roll plate itself. So I don't think that all hope is lost just yet on this. And again, with a heated bed design, it might be worth revisiting this in the future. So I think there's quite a lot of promise here of direct melting of molybdenum on tungsten. Yeah, so that's basically it. We've carried out a number of parametric studies. We've looked a little bit at the influence of feedstock. You know, these are challenging materials, but I think we're starting to get to grips with them. We've basically, under AMAZE, given sort of our best effort with the technology as it stands, but we are looking to the future and hopefully developing it further. On that note, thank you very much. Happy to take any questions.